Dr. M. Sundareshwari, Professor, Dean, School of Science and Humanities, Satyabama University. I am from the Department of Physics, and today we are going to discuss about the superconductivity and in particular about the BCS theory that explains how the superconductivity is possible in low TC superconductors. So, we will discuss about the first occurrence of superconductivity, when it has happened, in which material, who has discovered it. It has been discovered by Commerlin Owens in the year 1911 when he was trying an experiment with the electrical resistivity of metals. When he was doing his experiment with the metal called mercury, and he has kept the temperature of his mercury at 4.2 Kelvin, the liquid helium bath temperature, and he was taking the electrical resistivity measurement. When he plotted the graph, he found suddenly at 4.2 Kelvin there is a huge drop in the electrical resistivity, nearly 10 power 5 times the drop in the electrical resistivity, and absolutely the electrical resistivity was found to be 0. Even at 0 Kelvin, you will have some electrical resistivity in materials in normal conductors. Whereas see the green line, where this is for a superconductor, say at one particular temperature, there is a sudden drop in electrical resistivity where you have 0 electrical resistivity, which means you have enormous current there, and that's the materials we call by the name superconductor. And this temperature where this transition is taking place from the normal state to the superconducting state, this temperature we call by the name transition temperature. And this transition temperature for mercury, it is found to be 4.2 Kelvin for mercury. So, the first occurrence of superconductivity has happened in the year 1911 for the material. One centenary year celebration we have celebrated recently, so in the year 2011, about the discovery of superconductivity. So, now let us discuss about the Bardeen, Cooper and Sheriffer theory, say the BCS theory, where the scientist Bardeen, and then he got a Nobel Prize in the year 1956 for his discovery in the field of electric transistor. So, that time when he was actually going on for that function, the Nobel laureate function, he has been called by the king of that country, Sweden. The king was asking him, why you have come alone, why not you have brought your family, and he replied that I will bring my family next time. So, surprisingly, in the year 1972, he got the Nobel Prize for his discovery in the field of superconductivity. I am sharing this information for the motivation and the self-confidence that scientists had at that time, because he had got 2 times the Nobel Prize, Bardeen, Cooper and Sheriffer theory, and that much self-confidence he has got, and that should be inculcated in every student's life. And what is the motive for these 3 scientists to propose the theory is that when they studied the properties, it is found that in one of the property we will call by the name isotope effect. Okay, Tc into m power half is a constant. Tc I told you, the transition temperature. M is nothing but the atomic mass, the isotopic mass. So, once you have the name isotope, or once you have the name mass number, which means it involves the nucleus where we have the positive charge ions. So, it is very much sure, they are very much sure it is not only the electrons involved in the superconducting behavior, something positive ions is also involved. That much clue they have got. With that motive, they have proceeded in explaining the BCS theory as follows. And some prerequisite also we need. Conductor means what should be the theoretically how one has to look a conductor. So, for that I am telling that you imagine that we know very well the conductors, the atoms will be regularly arranged in a lattice. So, you imagine that positive ions are fixed to the lattice and the valence electrons are freely moving. Now, with one positive ion core, an electron is coming and hitting with that lattice, and initially you assume the wave vector to be k1, which means k, it is its momentum, okay, and while hitting it transfers some of the energy to the lattice. Initially the lattice is at rest. Now, what happens initially with the lattice when it is hit by the electron, it will get disturbed, okay. So, a part of the energy has been transmitted to the lattice, and now the lattice is getting distorted. In a vibrated state, say you will be attracted. Okay, that point you have to note, because so this electron number 1, after hitting it loses some energy and it is going like this. Okay, that is electron 1. Now your lattice is in the distorted state. So other electron is getting attracted because of this distorted lattice and comes in C. what is happening there. Now this electron will come here, because since it is in the distorted state, it will be getting easily attracted by this. So what happens now, whatever the energy the lattice has will be absorbed, will be taken up by the second electron, and the second electron is now with the wave vector k2 plus k. So you have two electrons now, electron 1, then the lattice vibration we call by the name phonon, PHONON, and then electron 2. So now in this process what happens now, energy has been transmitted from electron 1 to the lattice, and then from the lattice to electron 2. A has given something to B, B has given something to C, which means A has given something to C, which means there is an attractive type of interaction between the electron 1 and 2. So normally initially we told two electrons can never, because there is an electrostatic repulsive force, but through the phonon or through the lattice vibration, these two electrons, electron 1 and electron 2, can interact attractively. So these two electrons form a pair, and that pair has been named after the name of the scientist Cooper. And now here I am explaining for one Cooper pair. Imagine in the solid, in the entire lattice, so many Cooper pairs are, there is a possibility of formation of so many Cooper pairs. Whenever a Cooper pair is formed, the volume of the Cooper pair will be 10 power plus 6. It can encompass 10 power 6 other Cooper pairs, and they will move very slowly, they drift very slowly, cooperatively they will move in the lattice. They will move coherently. Okay, they will not hit with their neighbors, they will not hit with the positive ion, they move identically, they drift very slowly, they move cooperatively within the lattice. So you would have seen in the evening time in the sky, birds will be flying from, they will be moving from one end to another end. In a crowd they will be moving, they will not disturb with each others, they will move cooperatively. In the same way, the electrons will move with identical velocity, they will not hit with anybody else. So this movement of huge number of electrons, even a very small velocity, if they move, they will contribute a large amount of current. In such a way, the electrons will be moving, gliding, moving very slowly throughout the lattice without offering any resistance to its motion in the lattice, and that is how we have enormous amount of current called by the name supercurrent. That is why the Bardeen, Cooper and Schaefer have been awarded with the Nobel Prize. And to conclude, I would say that the applications of superconductivity is enormous. Say we have SQUID, SQUID, superconducting quantum interference device, where even a very minute magnetic flux lines can be detected, and it is used in the field of medicine. And we can give the example of Maglev train. In Japan we have the super fast train which will be moving in 1 hour 500 kilometers, that is the speed. So it is also magnetically levitated train. It is also working under the principle of superconductivity. In our next session we will discuss in detail about all the applications of superconductors. Thank you.